Hello everyone and welcome to a new lecture about artificial intelligence. In today's lecture, we want to learn reverse search algorithm, BFS. This is one algorithm in problem solving by search. So in the previous lecture, we learned about the four main categories of AI: problem solving by search, knowledge, reasoning, and planning, learning, and the last one is communication, perceiving, and acting. In today's lecture, we're gonna study problem solving by search algorithms. And in here, we learned that there are some algorithms like ASR, BFS, DFS, and they serve as the foundation for tasks like pathfinding, puzzle solving, and game playing. So first, what is problem solving by search? Problem solving by search refers to the systematic exploration of possible solutions, and in here, we want to reach the defined goal state. For example, solving a maze involves starting at an initial point, then we explore different paths, and we attempt to reach the exit. The fundamental principle here is to model a problem as a state space. In here, we have states like all possible configuration, for example, positions in a maze. We have actions that transit between states. We take an action, we move from one state to another state. Then we have a goal state. This is the desired state to be achieved. We want to finish it, right? So search algorithms are some AI techniques. They systematically explore solutions, and we want to find the best path to the goal. So the core idea here is we want to represent the problem as a state space, like state, action, and goals, and we want to apply search methods to discover optimal or feasible solutions. So we have agents here. Agents are some AI systems, and the agents model a problem as a state space, and they apply search algorithms to move from an initial state to the goal state. How? By selecting appropriate actions. We already know that there are two main categories for problem solving by search algorithms: uninformed search and informed search. Today, we're gonna learn uninformed search. In this category, the search process relies only on the information that explicitly given in the problem definition. In here, there is no heuristic guidance. And later we will learn here what is heuristic. The heuristic is to use to indicate whether a one non-goal state is more promising than other. But in here, we don't have a heuristic guidance. In other words, the search is completely blind. So uninformed search, or we can call it as blind search, it explores without any clue about whether the current path is likely to lead to the goal state or not. So within uninformed search, we have several important algorithms like breadth first search or BFS. These explore the search tree level by level. Then we have DFS, depth first search. DFS goes as deep as possible along one branch before backtracking. Then we have iterative deepening search or IDS. IDS combines the benefits of both BFS and DFS, and it gradually increases the depth limit. Finally, we have uniform cost search. This UCS expands the nodes with the lowest path cost, and in this way, it makes it suitable when actions have varying costs. So these algorithms that you can see here, they form the foundation of problem solving by search in AI, and they serve as the basis for more advanced, like informed search technique that we will explore later. So let's talk about BFS. BFS is one of the most common strategies for traversing a tree or a graph. As the name suggests, it explores the search space breadthwise. This algorithm starts from the root node and expands all successor nodes at the current level before moving on the next level of nodes. So first level, then second level, then third level. BFS is also an example of general graph search algorithm. It means it can be applied not only to trees, but also to more complex graph structures. To implement BFS, we use FIFO, first in, first out queue, and this is a kind of data structure. In here, nodes are explored in the exact order that they are discovered. Because of this behavior, BFS is guaranteed to find the shortest path in terms of the number of steps. That's why it provides all actions, because all actions have the same cost. And this makes it highly useful for tasks like pathfinding and problem solving in AI. So let's see how it works. So suppose we want to go from source to goal here, and there are some nodes in here. The key idea of BFS is to expand the shallowest node first. That means it always explores the nodes closest to the root before moving deeper into the search space. Suppose we are in here, so we have converted this graph to a tree. So this is search tree, right? So in this case, from S, we will go to D. We check whether D is the goal state or not. If not, we go to the same level. So we call it as, for example, this is level 0, this is level 1, this is level 2, this is level 3, this is level 4, this is level 5, and this is level 6. So first, we will go to D. D is the goal state? No. We will go to E. Is it the goal state? No. We will go to P. Finish, then we come to here, right? Breadth first, right? So for this one, we maintain a fringe. What is the fringe? The set of nodes waiting to be explored. And here we follow a FIFO, first in, first out. This ensures that nodes are expanded in exact order they have been generated. It's important to know that while BFS often looks like a tree traversal, in practice, it can also be applied to graphs as well. This means that there may be cycles in the search space. So here we go. This is the S, right? First level. Then we go to A. Then we go to B. Then we go to C, D, G, H. Then we go to E, F, if our goal is this one, we will stop here, because every time we check whether the goal is. So in this example, if this k, we will be here after traversing all. So what is the meaning? What is the usage, right? If you remember, we had this problem, right? So this problem. So in here, this is the initial state, right? Initial state. And so everyone is a node, right? Right? All of them are some nodes. So based on BFS, first we go to this one, whether we check whether this is a goal state or not. If no, we go to this one. It means 6 already down. Then we go to this one. It means 5 goes to this part, right? So we check one by one to reach this goal state, right? So this is the goal state. Let's now explain the properties of BFS in more details. First, what nodes does BFS expand? We want to check, we want to evaluate the performance of this algorithm. We want to see whether it's a good algorithm or bad algorithm, right? So this algorithm processes all nodes above the shallowest solution. So if we let the depth of the shallowest solution be S, we show it by S, and then the search will take time proportional to BO of B in power of S plus 1. What is the B here? B is the branching factor of the tree, right? And then BS, B in power of S. So in the level 0, we have 1 node. In level 2, we have 2 nodes, right? In level 3, we have B power of 2. So B power of S, if B power of S is the number of nodes in the S level, so we can write this one as, so sum of them, right? 1 plus B squared plus up to B in power of S. And we can rewrite this one as B in power of S plus 1 minus 1 divided B minus 1. This is the number of nodes, right? So the big O, or the search time, or the time complexity, big O, B in power of S plus 1. This shows that while BFS is complete, it can become computationally expensive, because when we have depth, we have too many levels, then it takes a lot of time. So the next thing is how much space this algorithm requires, right? So because the fringe contains roughly the entire last tier of the tree, its space complexity is also B in power of S plus 1. This is actually the main drawback of BFS, because this requires a lot of memory. So is this algorithm complete? The answer is yes, right? The answer is yes. If we have S is finite, and if there is a solution, so BFS will find it finally. And BFS is optimal. It is optimal only if all step costs are equal, right? It means moving from 1 to 1 is the same, such as when every action has a cost of, for example, 1. So in those cases, BFS guarantees the shortest path in terms of the number of steps. However, if actions have varying costs, it means taking different action has different costs. For example, moving from one city to another city, BFS may not return the optimal solution. All right, so now let's calculate the time and memory that we need for BFS. Suppose B is equal to 10. This is the branching factor, right? And here we have R. So R is equal to 200,000 nodes per second. And this is the memory required for each node, 100 bytes per node, right? So the time that, so we at the depth of 0, we have 1 node, right? So we can calculate the time like this as 5 microseconds. How we can do this one? We can go and find out time is equal to, for example, 1, and this one divided by 2 in power of 2 multiplied 10 in power of 5, and which give us this 5 microseconds. For example, at the depth of 8, right? So in here, time, so we have 10 in power of 8 nodes. Time is equal to 10 in power of 8 divided by 2 multiplied 10 in power of 5, right? This one is 2 multiplied 10 in power of 5, right? And this one will give us like maybe 500 seconds, and which is equal to 9.25 millimeters. So you can calculate for the rest. In case of the memory, BFS must store the fringe, the current frontier of the node at the deepest level explored. At depth, like S increases, the fringe size is roughly the number of nodes at that depth. So we can say in here, fringe size is equal to B in power of S, right? So if each node requires 100 bytes memory, then the memory is equal to B in power of S multiply M, right? For example, for this case, at the depth of 12, we have 10 in power of 12, right? Then we can calculate like this. The memory that we need, memory is equal to 10 in power of 12 and multiply 100, right? So 10 in power of 12 multiply 100 is 10 in power of 14. This is in bytes, right? So in bytes, for that one, we need to divide by 10. So 10 in power of 14 divided by 1024 to convert bytes to kilobyte, then do again to megabyte, to gigabyte, to terabyte. Finally, you can come up with this 100 terabytes. So lastly, let's look at the advantage and disadvantage of BFS. On the positive side, BFS has 2 very strong properties. First, BFS is complete. It means if a solution exists, BFS is guaranteed to find it eventually, right? So BFS will provide a solution if any solution exists. Second, if there is if there are multiple solutions, more than one solution, BFS will return the node that requires the fewest steps, the least number of steps. In other words, BFS provides a minimal solution in terms of depth, which is very important for problems like pathfinding. But BFS also comes with significant drawbacks. The first drawback is high memory, right? It requires high memory because BFS must store all the nodes at the current level before moving to the next. The memory usage grows exponentially with the depth. This makes it impractical for large or deep search spaces. The second drawback is time. If the solution lies far from the root node, BFS may need to explore a huge number of states before reaching to the goal state. So, in conclusion, while BFS is both complete and optimal under unit step cost, it means every step has the same cost. In practice, it is often limited by its exponential time and space complexity. Okay, thank you very much for your attention. Please feel free to ask me your question. Thank you and see you in the next lecture.